Good morning, ladies and gentlemen. Thank you for making time to follow this presentation. My name is Teodor Andron. I'm a PhD student at Jožef Stefan Institute in Slovenia. And thanks to our collaboration with PS Analytica from England, we made this beautiful piece of work come to reality. So let's go directly into our presentation. An improved remote sampling technique for atmospheric pollutants. Now, in order to say if it is improved or not, we have to say what we resolved. Now, when you're thinking about monitoring atmospheric pollutants, in the urban areas, there is not many problems. But when we move here's where the problems arise. Mostly because there's a lack of infrastructure, so we do not know exactly if we can get the gases that usually devices work with on there. Where do we get electricity? Do we even have roads to get to the interest points and so on? So when we go into remote areas, we have different problems and it limits the hardware viable for this solution. Now, in remote areas, the most commonly used are passive samplers. So, in theory, they're simple. It's just a cartridge inside which we put a sorbent material that samples and retains our analyte. It's called passive sampler because the air goes passively through the cartridge. And after it has sampled enough time to have a quantifiable amount of our analyte on the sampler, we take it to the lab, we analyze it, and then we get a result. Now, the result always comes with an uncertainty, but the uncertainty is not limited to just the standard deviation or the repeatability of our results. In the case of the passive sampler, while it is pretty easy to determine the mass of the sampler, there are some issues regarding with the sampling rate. So the sampling rate can be influenced by pressure, temperature, humidity, wind, just to name a few. And if you don't monitor these things, you do not know exactly what the sampling rate was. Now, the passive samplers are calibrated at the different manufacturers in ideal laboratory conditions. And if you give them the data for these atmospheric variables, they can calculate the sampling rate for you, but they're pretty secretive about the formulas that they use. So in order to reduce the uncertainty coming from these variables, we came up with a solution. But we have to understand first exactly where is the problem. So in our case, the experiments we did were on atmospheric mercury. So the concentration of mercury is usually mass of mercury per the volume sampled. And if we calculate these terms based on calibration curves, then we have the top part, which is practically the mass of mercury, which has been calculated with the calibration curve. And then we have the sampling rate, which was also calibrated based on a calibration curve or a certain type of calibration. And then the sampling rate, you take the average and you multiply it by the time that has sampled. And this is how we get the calibration for each of the terms. Now, what we want to solve is the uncertainties coming from the calibration of the flow. And the solution is to go solar. So in remote areas, you do not have electricity, but you have solar power. The solar power will recharge a lithium-ion battery, but what will the lithium-ion battery power? Well, a micropump. So the micropump is there to give us an active sampling throughout the cartridge of whatever sorbent material we use. But the key here is that we attach a data logger to the micropump. So the idea is that once we get the voltage from the pump, we can back calculate the sampling rates throughout the sampling periods. And why we need this is because it is not connected to the DC or the electrical socket. The voltage in the pump constantly varies, and so the sampling rate constantly varies. And how do we solve this issue? I'll show it through the model that we used. So this is practically the final product that we have. We start from the solar panel, which just powers the ion battery, which is behind the device. And this lithium ion battery powers the pump. The pump, which has attached to it a data logger in order to get the voltage. So the pump just gets the air going through the sampling material right here. We used Amasil gold because we were sampling mercury, but theoretically you can put whatever sorbent material you want. Now, the key to this whole calibration are these two little fellas here. So those are the voltage calibration points where we can change the voltage throughout the pump in order to measure the sampling rate at certain increments of the voltage. And how it looks in the end is like this. So this is a calibration curve in which we vary the voltage, in order to see how the flow is at certain increments of the voltage. And then when we get the data from the voltage from the field, then we can back calculate the sampling rate for the whole period of the sampling period. Now we use this from this data. So this is the data actually that we use on the calibration points. Mainly what people would be concerned with, well, it's a remote area, no electricity. How long can this device go? And now, for example, here we have a test for 20 days, but we did not stop it because it ran out of juice. We stopped it just because we proved our point. Because we have up to 200 milliliters per minute of sampling rate, then we do not need weeks and months compared to the passive samplers to get our analyte on it. And what you see here is practically the data that we incorporate in the calibration curve. So it's the voltage going down and up, because it's depleting the battery and then recharging, depleting and recharging. And of course, for those wondering, well, if there is absolutely zero light, we charge the batteries and we let the system go. And we saw that the system can go just over 6 days with no sun in the laboratory. And may I remind you that all these experiments were done in London. So if it can go 20 days in London, I'm pretty sure it can go for an indefinite amount of time. On to our validation then. So in order to validate these pumps, we took two such remote sampling powered solar powered systems, and we put them to sample for 1 week in parallel. Along with them, we also placed two mains pumps. So these are pumps that were connected to the DC and were sampling in the same time as the solar power system. So the only difference between them is in this part. So from a DC micro pump attached to a solar panel, now we have a pump which runs on DC current. And we also have an MFC or mass flow controller in order to set the sampling rate similar to the one for the solar power system to have a more representative comparison. And in the end, we also set an online mercury analyzer, which practically is a Sir Galahad, its name, which samples every half an hour air, and then it thermally desorbs the mercury and analyzes for atomic fluorescence spectrometry. And then what we practically did, we took these half-hour measurements over the course of 7 weeks, we averaged it, and then we compared it to the results that we got from the pre-concentrations method that we have in A and B. And what did we get? Beautiful comparison. So the first two columns are practically the solar-powered pumps, followed by the remote sampling with mass flow controllers, and in the end, the online mercury analyzer. And from some first tests, we were actually thrilled to see that there is a really good agreement. Now, the error bars represent the uncertainty estimation of the results at a coverage factor of 2. Now, there is a long discussion here because normally we should see some higher uncertainties coming from the solar powered pumps and the remote sampling because of the repeatability. But due to the fact that we only have one measurement per each system, we cannot actually calculate any repeatability because it's a pre-concentration technique. And so we see that both in the indoors and the outdoors measurement are really satisfying, especially for a first product. And on to this, PS Analytical, 1 year after these results that I just showed, they started to do parallel sampling for 1 month periods. So the two solar power system, they just install them, and every month they do sampling. And we can see that they are pretty in a very good agreement from sampler 1 to sampler 2 with a really low standard deviation between them. Yeah. So on to the uncertainty, yeah, to whom it may concern, what we take into account when calculating the uncertainty from the solar panels is practically the mass of that we use during the calibration, the concentration of the standard coming from the bell jar system, because the atomic fluorescence detectors were calibrated with mercury 0 from the bell jar. And also, this is the problem and the element that we cannot include in the pre-concentration techniques, mainly the repeatability. Yeah. And of course, we have uncertainties coming from the measurement of time, the certificates of the pump, and also the sampling rate of the pumps. This being said, we are very delighted to see that we managed to make a sampling device that goes actively and autonomous in remote areas and that can be used further for atmospheric analyze, thus improving the intercomparison campaigns and even the atmospheric models, because the passive samples may not give the desired results. In conclusion, we made a cheap, easy-to-use sampling system for atmospheric pollutants in remote areas, which has a reliable calibration for the sampling flow, which was missing until now, and it works in non-stop cycles, even through bad weather, because it's worth mentioning, even if there were a bit of clouds, we could see that the system was still charging. So if it's really, really dark, of course, you cannot see anything, but if it's just a bit of cloud, there is no problem because the system was still charging. Thank you very much for your attention. I hope everything was clear, and if you have any questions, please ask.